starting from yesterday, we talked about chapter 3, and this is a motion in 2 dimensions, right? So again, our goal here is to talk about kinematics, which is how to describe motions, and basically yesterday we kind of talked about the mathematics about vectors. Okay, remember vector is something has both magnitude and direction. So let me maybe write here again. Oh, okay, I forgot to. Okay, let me see. What? There's something wrong with my okay, here I think. Oh, okay. Okay, here we go. So it has magnitude and direction. That means when you try to, for example, when you try to add vectors together, it's not that trivial because when they point to different directions, how do you add them, right? Now, as we discussed yesterday, the right way to add them is that you have a single vector as the sum of the two that represent the same effect as the two vectors combined. So for example, you have one displacement, another displacement, just draw them next to each other so that you can, this is gonna be your sum vector because it do the same thing. It brings the object from the initial point to the final point, just like this two vectors does. Okay, so, and then we talk about basically all kind of operations. And again, the most important one is the addition. Well, subtraction you can do just like doing addition by you just add a negative vector. Okay, I mean instead of subtract the vector, you can add the negative of that vector. Okay, and then multiplication is by numbers, again pretty straightforward, intuitive. Just if you have 3 times that, just add 3 of them together. Okay, so and then we did one very quick exercise, and then the second part we talk about component method. This is the previous thing. All we're talking about here is the geometrical definition, but if we want to get numbers, right? We need to use a component method. The basic idea of component method is you draw all the vectors in coordinate system like this, you know, and based on the coordinate system, I mean, you find the components like ax, ay, bx, by, and then after you got the components, you add the components together. Okay, cx is just ax plus ay, and cy is ax plus bx, cx, cy is just ay plus by. So we did an example here, as you can see. And well, and then we also did a exercise like toward the end, right? So that's what we did so far. Okay, now today let's continue. So as I said, we did some exercise yesterday, but we didn't have enough time. So let's do some more exercise here. Again, remember you got your bonus point by doing those exercises. Okay, so another exercise we can do here is this. Okay? So as you can see here, right, the essential part of adding two vectors, two-dimensional vectors, are not that hard. If you know the components, you just add the x component and y components correspondingly, and then you got the two components of your sum. The actually complicated thing comes in when you need to convert from length and angle to these components, or sometimes you need to convert it back. Okay, so let's do that. Okay, let's do one exercise for each. So let's consider a vector in the third quadrant. Okay, say you have this vector here. Okay, it's called vector A. Okay, let's say suppose we know the length and the angle of the vector. So the length, let's say, is 3 unit, and then angle is gonna be again I mean the angle you should always refer to when you draw a vector in the coordinate system is the angle referred to the positive x direction. Okay, so for a vector in the third quadrant, it could be anything between 180 to 270. So let's say this is a I mean, let's say 210, maybe 220 degree. Okay. Okay, suppose you're given this vector, okay, 3 unit, and then the angle is 220 degree. Okay, let's try to find out the two components of these vectors, okay? Try to find AX and AY, okay? Now, again, you can refer to what we did yesterday, the example to calculate that. Basically, you need some trig functions here for AX and AY, okay? And let's do this one first, and then we'll do another one, okay? Let's see, maybe we can do both. Okay, maybe let's do, maybe let me write down all these two exercises, and then we can, you guys can do both, okay? Just finish the first one and then tell me your answer, and then go ahead and do the second one, okay? In the second one, we'll do another, we'll do the opposite, okay? Suppose we got the vector in components. How do we convert it back to length and unit, length and angle, okay? Suppose you have vector like this, okay? Okay, I'm gonna put it in the second quadrant for some reason. Let's see, yes. Okay, let me do this one, okay? Suppose you have vector like this, okay? Let's call it B, okay? Suppose you're given Bx equals to -2 and By equals to 3. Okay, notice that this is negative because the X component here going to the negative direction, okay? So say you have this two. Let's try to find out the length and angle of the vector. Okay, so let's do this too, okay? Go ahead, and again, after you got your answer, send me a message. Okay, let's talk about this together, okay? Again, you should keep in mind, these problems that we do in class are not the ones that you're supposed to get it right. It's not a test, right? It's just something I want you to practice on what we just learned so that you have a good idea. You need to try, you know? Well, if you feel like a little bit frustrated about not getting it right every time, you shouldn't feel that way, because that's whenever you get it wrong, that means you need to learn something, right? This is a learning process. So you have to almost like you definitely get it wrong, you know, otherwise you won't be here. You should be in a different class, you know, higher level class, okay? So again, don't feel bad, you get it wrong, just keep trying, okay? That's the key, okay? And after a while, you feel like you learn a lot, you know, if you don't try it, you won't make mistake, you feel good, but you don't learn anything, okay? So let's talk about these two, okay? First of all, this one here, okay? So it gives you the 3 units and 220 degree. Well, there are two ways to do this. One way is to use the formulas we kind of derived already. Just write AX equals to A times cosine theta. It's always the length times cosine of the angle. And then you should use the angle between this vector and the positive X direction. So you should have 3 cosine 220. And this gives you negative 2.3, okay? Or negative 2.298 or something, okay? Now, AY equals to A sine theta, which equals to 3 times sine 220, which is gonna be negative 1.9, okay? So these are the correct answers, okay? Well, you may feel like, I don't remember these formulas, okay? So you don't have to memorize it, right? So as I said, so you can easily draw it using the right triangle here. Let's say, let me do the a little bit differently. So if you look at this right triangle, right? See, this is your vector A. Now, if you draw a line like this, right? This length here is going to be your AX, and this length here is going to be your AY, right? So if you just look at the triangle here, if this angle is theta, then certainly AX, okay, using the trig function you learn, okay? If you know A and theta, then AX is just AX over A is cosine theta, and AY over A is sine theta, okay? Okay, so because this is adjacent divided by hypotenuse, that's cosine, offset divided by hypotenuse, that's sine, right? Now this is gonna give you the correct formulas like you're doing here. So you don't need to memorize those formulas. If you just know the definition of the trig function, you know. So you got this, okay? Now, if you want to consider, you can do just consider this triangle itself. Then the angle in here is certainly an angle smaller than 90 degree, right? So this is 220 in total, but this part here is 180. So this angle itself is only 40 degrees. So If you use 40 degree here for this angle, you can calculate these components, but you're not gonna get the minus sign. So you're gonna 3 cosine 40, and this is gonna be 3 sine 40. In both cases, you're gonna get positive numbers. So you're gonna get positive 2.3 and positive 1.9, okay? That's because you use this angle instead of the actual angle in the coordinate system, okay? Well, if you use these are good, but if you, then in the last step, you should notice this vector is the third quadrant. AX certainly going to the negative direction, AY is going to the negative direction as well. So you need to actually, so these are actually, what you're calculating here is the absolute value. So AX actually equals to negative 2.3 and AY equals to negative 1.9. Well, these two minus signs you see from these from the picture here, okay? Now let's talk about the second one, okay? So you're given the two component BX and BY, and because the X component is negative, Y component is positive. So certainly this vector is in the second quadrant, okay? Now, again, you can form a triangle here to calculate the, so this is your B, your BX, and your BY, okay? So what you have is BX equal to negative 2, BY equal to 3. Okay, negative 2 and 3. So, and okay, let's first calculate the, okay, this is the angle. Calculate the length. Well, you can use Pythagorean theorem. So B equals to BX squared plus BY squared and then square root, right? So that gives you negative 2 squared plus 3 squared. So that's 4 plus 9, so it's 13. So square root 13. You use calculator, you get like a 3.6, okay, for the length here. For the angle theta here, given BX and BY and BX, we know that theta equals to okay, tangent theta, okay, equals to BY over BX, okay. Now here again, there's two ways to do it. One is to plug in those components directly, so you have tangent theta equals to 3 divided by negative 2, right? That's like negative 1.5, right? And then theta equals to tangent inverse negative 1.5. Okay. Now here's the thing. Okay? If you do this on your calculator, you get angle, you get negative 56.3 degree angle. Okay. Well, this angle is not correct. Why? Because based on the convention here, right? So when you have a like, let me use the draw new one. When you talk about angles in the coordinate system, the convention is when the angle go counterclock, starting from the positive x direction, when the angle go counterclockwise, it is positive. Okay. When the angle go clockwise, it's negative. So negative 15.6.3 means that the angle is actually going like this. Okay. So you're gonna have a fourth quadrant vector. Well, it's pretty clear from the diagram we have here, right? It is second quadrant. Even without the diagram, because you know the two components here, right? The x component is negative, y component is positive. So the vector is in the second quadrant, okay? Now, how come your calculator does not give you the right answer? Well, this is why human beings are still smarter than, at least we're smarter than your calculator. Maybe not for smarter than some computers, but at least for the calculator, okay? The problem is this, okay? The problem is there is ambiguity when you take a tangent, okay? So for example, if you take tangent negative 56.3, you get back this negative 1.5. However, if you take tangent of 180 plus 180 minus 56.3, you also get negative 1.5, okay? So both these two angles have the same value, okay? So when you start to do the inverse, if you start from this value and then do the inverse, okay? So this angle here is actually 123.7 degree, okay? So when you do this inverse, your calculator only gives you one value instead of two values of the angles, okay? And by default, it gives you this angle instead of that angle, okay? So your tangent inverse on a calculator, sorry, not theta. It's something. It gives you something like a theta, right? An angle. By default, it stays range from negative 180 to okay, sorry, negative 90 degree to 90 degree. Okay, so whenever you take tangent inverse, it's only gonna give you one value, and that value will stay between negative 90 to 90. So that's why when you take tangent inverse, in this case, it gives you negative 56 instead of 123.7. Okay, now these two angles, negative 56 and 123.7, they're two angles up by 180 degrees. So it's the opposite direction here. This one here is that one 123.7. Okay. Now, how do you know which value you should choose? Well, again, it depends on the components you're given. So the component you're given right now, this is a -2, this is 3. That tells you it's in the second quadrant. The vector itself is in the second quadrant. You can draw roughly where the vector is based on these two components. So that definitely tells you this angle here, negative 56, is not correct. You have to add 180 to it. You have to make it 123.7. Okay, that makes sense, you guys? Well, there is this ambiguity for tangent. With you may say, what if I use sine or cosine? Can you sine inverse or cosine inverse? For example, in this case, to get the same angle, you can use sine inverse. By over b, or cosine inverse bx over b. Okay, you can do this. Okay, however, each one of these has ambiguity. Okay, maybe not for this specific case, but for other for a vector in some other quadrant, there's always going to be ambiguity here. Okay, so each case you need to deal with this. So the best way to do it is this. Okay, first of all, take tangent. Okay, inverse. Okay, get the angle. Secondly, draw the vector based on this angle. See whether that is the vector you're looking for. Or if you see that it's actually going to the opposite direction, you need to add 180 to it, okay? So you have to draw it to see whether this angle is correct or not. In some sense, vector is a geometrical object. So in order to see where the vector is still the best you can draw it, okay? You don't need to draw it very accurately, but at least it give you some quantitative information, okay? Well, another way to do this, do the same thing for the angle is again, let me put method 2 here, okay? Okay. Method 2, okay? Well, very similar. So basically, again, you have this triangle here, but when you calculate the angle theta, just consider this as a triangle, so the lengths are all positive. So I'll just put 2 and 3 here, okay? So by doing tangent inverse of this, 3 over 2, you definitely get a positive angle, okay? So like tangent inverse of 1.5, okay? Let's say what do you got, okay? Tangent inverse 1.5. You got 56.3 degree. Well, you do this method, you get this angle right here. This is a geometric angle. It's definitely going to be smaller than 90 degree because the total here is just the 180, right? So this is 56.3 degree for this angle. Okay. Now to figure out the actual angle here, you draw this back into the coordinate system. Now you're seeing that you get this angle here, right? 56.3, right? Because that's the angle from the triangle. Well, the actual angle you want to get is this one here. Well, that certainly is just a 180 minus 56.3. And that certainly gives you 123.7, okay? Again, either this method or that method work. It depends on which one you feel more comfortable. If you feel like it's kind of complicated to figure out, to trace the signs and everything, you could choose to do everything just like a geometrical figure, just calculate the angle in this figure, and then in the end, go back to the coordinate system and specify the angle that you want, and then find the corresponding angle, okay? Or you can just do this, okay? Either way. Okay, is that clear for you guys? Any questions? We're good? Okay, great. Yeah. See, I really enjoy teaching a small size class because I can easily get feedback from everybody. You know, it's way better than teaching a large class. Okay. So anyway, so we're done with this part. Okay. So to summarize, we learned about. So this is part one. Part one of this chapter has been done. Okay. As I said in the book, this part is located in your introduction chapter one, but we did it in this part. Okay, so we talked about vector calculation, and mostly the most important one is vector addition. Okay, I don't know. There's something wrong with my stylus. So vector addition is the most important one, and we see that how to add vectors to vector geometrically like this. You know, draw first vector, second vector, and then the sum like this. You know, connecting the starting point and end point, or algebraically, or to get a number, we use component method. Okay. There's something wrong with my stylus. So we use component method. Okay. So in the component method, there's essentially just three different things you do. The critical step here is to add the x component, y component correspondingly to get your component of the sum. Okay. However, in order to get the x component, y component, sometimes when you do like this, you know, given the length and angle, we need to find the component. Okay. And sometimes after we got this component of the sum, we want to get the length and angle. So we need to do something like this. Okay. So this is three different parts of the whole thing. In the most complicated problem, you may need to do all the three parts. Okay. So it is more complicated than simply adding two numbers or two scalars. Okay. That has only magnitude. It is more complicated, but it's not infinitely more complicated. Okay. Another thing is, in this chapter, I mean, for vectors themselves, I want you guys master all these three parts. But for applications, actually, it turns out that a lot of times the concept component method is very important. And a lot of times what we mostly need is this first way of doing it, you know, basically finding the components given length and angle. And the same thing we'll need for our chapter 4 when we talk about Newton's law. This is again very important thing. So we need to work with vectors a lot in this class, and that's probably the biggest challenge for you guys because this is totally new for you. You haven't learned this math before, so it's what makes it complicated. Okay. So, but hopefully by doing the homework and practice on it, you get it. You know. Okay, so let's go to part 2 now, okay? Part 2, okay? So in part 2, we're gonna actually start to apply what we just learned about vector stuff to two-dimensional motion, okay? And as we learned from, excuse me, last chapter, we have like time, displacement, velocity, and acceleration as our quantities to describe kinematics, describe motion. Turns out that in 2D motion, all of these are still useful quantities. And that's why we learned it in the first place in the first, for 1D. And it's just like, wait, I'm sorry. Okay. So it's just like, we don't need that. So in 2D, this is 1D, okay? In the case of 2D, we still use them, but we use them a little bit different. We use a little bit different notation. So instead of call it X, we call it R. Well, X is more like the X component. So, and then we put an arrow on top of it to remind us that we have vectors. And all these are, all the definitions are still applied. So for example, the displacement of a motion still given by is the final position minus initial position, okay? Well, velocity is still defined as delta R over delta T. And acceleration still defined as delta V over delta T, okay? So formally, by looking at these formulas, they look very similar, you know. It's just we use different notations, like and then we put an arrow on top of it, and it seems like it. But actually, in terms of calculation, it's actually certainly way more complicated. For example, for the displacement, right? Say right now, what we have is this. Okay, picturized like this. So suppose you have a coordinate system like this, and you have a motion like 2D motion like this. You know, well, what is the displacement? So this this is going to be, let's say this is your initial position Ri, this is your final position Rf. So the subtraction we have here is not totally non-trivial, right? It's not just subtract one number from another number. Essentially, we use the vector rule to do this, and then it turns out that the delta R is going to be given by this vector right here. This is going to be your delta R. Okay. Okay. Well, this all sounds like, I mean, same thing. If you want to calculate velocity, right, you need to use the vector subtraction here to get this delta R, and then similar here to get acceleration, you need vector subtraction to get delta V. Well, you may say, wow, this is too complicated. You know, how do I read? I mean, it seems like it's impossible to do any actual problem or anything about it. So it turns out that it's a little more complicated, but it's not too much. Okay, so the idea of to consider a two-dimensional motion is actually, I mean, it turns out it's not that bad. I mean, the key idea here is to use the component method. Okay, use component method. Okay. So this component method here serves for us as a way to look at a two-dimensional problem. So what do we mean by that? For example, if you look at the displacement delta R, you can write this as the sum of the two displacement along the x direction and y direction. These two are like the two components of the displacement, right? So see, here is your delta R. So if you have delta R like this, you can look at their components separately. This is going to be your delta x. This is going to be your delta y. Okay, and similarly, when you talk about velocity, you can write this as your two component. V. Okay, maybe let me use my eraser. So your velocity v, right? You can write this as vx plus vy. Okay. Again, this is like two components. Okay. Now each one of these actually is related to the two components of the displacement. So you can write like delta x plus delta t divided by delta plus delta y divided by delta t. Okay. Now similarly for acceleration, you can write this as ax plus ay, or delta v over delta t, vx over delta t plus delta vy over delta t. Okay. Now, see, notice that after breaking down to the components, see the x components right here kind of work separately from the y component. These two are totally independent from each other. So, and in some sense, after we do this component method, the two-dimensional motion we have essentially break down to two one-dimensional motions. See, this is a 1D motion formula, right? As we had before. This is another 1D motion, okay? It's just like one motion happens along the horizontal direction, one motion happens along the vertical direction. These two do not interfere with each other. They just work kind of independently, separately, okay? Does that make sense? So in this sense, we can say that one 2D motion is equivalent to two 1D motions, okay? So it's like it's equivalent to two 1D motion, one along the x direction, one along the y direction. Does that make sense to you guys? So this is our basic approach, okay, to a two-dimensional motion, okay? we always use component method. We always break down all the vectors into their x component and y component, and we always look at their components separately. Okay, we look at the x component and then the y component separately. Okay. Okay, so with this kind of idea in mind, let's talk about some specific kind of 2D motion. Okay. Actually, we'll start from a very simple 2D motion, but it's almost, but it's also a pretty interesting one. It's called projectile motion, okay? So we'll stay with this. This is kind of like our example 2D motion, okay? So what is a projectile motion, okay? It is very similar to a free fall motion that we talked about before. Let me turn off my back. So let's say I have a ball here, right? If I threw the ball, like say before we drop the ball like this, right? This is a free fall, right? If you toss the ball upward, it's a free fall. Now it's all one-dimensional motion. Okay, what about projectile motion? Now you toss the ball up, but you don't toss it vertically. You toss like, you give it like this, give it like initial like this. See, this is a projectile motion, okay? Well, obviously this is a 2D motion because it moves in a two-dimensional plane. It's not single dimension, right? Like this or this, right? It goes like this. Well, you can throw it horizontally like this. That's still a projectile motion, okay? So the projectile motion is actually one that we see a lot, okay, in our everyday life, because this is, whenever you throw something out, like a baseball or football or basketball, or you kick the soccer ball, they're all like projectile motions, okay? So, so basically projectile motion is something like have a trajectory kind of like this. It's a really nice, simple curve. It turns out it's a parabola, okay? It's a mathematical curve, parabola. We'll kind of explain why it's a parabola later, okay? So for now, let me ask you guys one question about this projectile motion, okay? So I have two balls here, okay? Again, you understand already, like before, right? If I drop the ball, two balls same height, they're gonna fall to the table same time, right? This is because they're both moving with constant acceleration 9.8 meter per second squared, okay? Now, here's a different question then, okay? So what I'm gonna do right now is I'm gonna drop these two balls, okay? But I'm gonna drop this one as before, like I could go vertically, but I'm gonna, for this one, I'm gonna give it initial velocity horizontal, like this, okay? I'm gonna throw the ball like this, okay? So it has a velocity like this. So then this ball is gonna go do this free fall motion. This ball is gonna do this projectile motion, okay? My question for you guys is, which one will fall to the table first? The baseball or the tennis ball? Okay, again, tennis ball doing like this, and the baseball going vertical. Okay. Send me a message. Okay, tell me what you think. Okay, I got one answer. Okay, again, you may not guess it right, but just tell me what based on your intuition. Okay, I got two answers. Okay, three answers. What about the okay, vertical? Okay, four answers. Okay, I got four answers. Okay, I got all of the answers. Okay, one person says they're gonna fall at the same time, hit at the same time, and then the others are saying that the baseball is gonna fall first. Okay, again, without further discussion, I kind of assume that maybe you guys think the baseball fall first because it's shorter distance, right? Well, let's do this together. Okay, again, it's not gonna be very accurate. You can do it at home. Try to be more accurate. I would try to do it horizontally. What do you think? Okay, it's the same. If you can start from a little higher position so that I can fall, but because the camera and the table I have here, I started pretty short, so it may not be easy to tell any difference, small difference. But our demonstration here, they focus on the same. It's kind of a little bit surprising, right? Why does it fall at the same time, right? Uh, shouldn't they fall like with different I mean the rate or something? Okay, so let's explain this. Okay, so this actually comes in of this component method we've been talking about. So think about this case, right? You have one ball going down, the other ball going this way, you know. These two motions look very different, right? This is a one-dimensional motion, this is two-dimensional motion. Okay. However, if you think about these two motions, I mean this projectile motion using the component method, okay. So along the vertical direction, okay, break down this whole motion into two different motions. One is the component along the horizontal direction. The other one is a component along the vertical direction, okay? So along the vertical direction, right, it looks like nothing but free fall, you know? You agree? It's in the air by itself. There's nothing touching it, right? So although it's moving, the whole motion is like this, but along the vertical direction, it does exactly the same thing. It should does the exact same thing as free fall, based on the component method, because these two components are totally independent from each other. So along the vertical direction, this thing does exactly what this thing does. Okay, so that means given any moment there, see, like later is gonna fall to here. Well, this one here is gonna be here. Okay. However, along this one moves the same vertical distance as this one, because along the vertical direction it's the same motion. Okay. Later on, it may go to here, and this one goes to a very different location, but this horizontal vertical distance are the same for both two motions. Does that make sense to you guys? Okay, so, and this is actually this is the idea approach we're going to use to study the projectile motion. Okay, so what we're saying here, if you break down this motion into two components, okay. Two components. Okay, let's basically say this is the y x direction and the y direction. Okay, or we don't need that. Okay, let's just say that. Okay, let's say that I mean, so along the vertical direction, it is a free fall. Okay, so that means it is a constant acceleration motion. Well, along the horizontal direction. Okay, so what happens along the horizontal direction? So basically along the horizontal direction, this is going to go like this, right? Well, again, we didn't really learn anything about the reasons for the motion, but actually it turns out this along the horizontal direction is a constant velocity motion, okay? There's no acceleration, okay? And certainly this is under the assumption that we can ignore air resistance as we always do for these small objects, you know? So this is basically the key for the projectile motion. It's nothing but these two kind of motions. Along the vertical direction is constant acceleration motion. Along the horizontal direction is constant velocity motion. And by the way, these two are the ones we learned from our chapter 1, right? 1D motion. So these are the two simple, the two simplest possible 1D motions that we can have. So when we combine them, we got this projectile motion, okay? Like we're talking about, okay? Well, you can think about an even simpler, a simpler 2D motion. That would be both, along both directions, you have a constant velocity motion, okay? Well, that motion is, I mean, it's the simplest, but what is the trajectory will look like, because both the two parts of motion is a constant velocity, so you're gonna have a straight line here, okay, for the motion, okay, and actually because you have a straight line, you actually can change your coordinate system from the original coordinate system like this to like this, you know, x prime, y prime. Then your motion is gonna happen along the x prime direction all along. So that's become a one-dimensional motion again. So that's why we don't talk about this one, because this is essentially, it can be converted back to a one-dimensional motion. So this one here is the simplest non-trivial two-dimensional motion we have, the free fall. I mean, sorry, the projectile motion. Okay. So with that in mind, let me see. We're ready to do some example, okay, for projectile motion. Okay. Let's see. Let me pull out the preview. And let me pull out the textbook. Okay. Wait, okay, let me better just go to here. Okay, right here. Okay, so let's go to chapter, this chapter here. Okay, so let's talk about a example here. Okay. 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 See this book here. Okay. Maybe let me try to explain this. What happened in general, and then we'll explain that. We will do a specific example, like example. There's a long jump motion or explorer, or like I'll do the long jump one. Okay. Let me explain this motion qualitatively first. Okay. So let's try to understand why you have a curve like that. Okay. Projectile motion. So let's say, suppose you threw the ball from the ground, okay, at the very beginning, you have the velocity like this, you know, v. Again, you try to separate these two components, like this is x and this is y. So your velocity can be, you can draw the two components of your velocity, okay? This is gonna be your vx, this is gonna be your vy, okay? Now think about it. What's going to happen to these two components, right? Along the horizontal direction, we said this is a constant velocity, so it's going to stay this. Keep at this same component. But along the vertical direction, the velocity is going to decrease because this constant acceleration going downward is 9.8. So if you throw the ball away, in the later time, Vx is going to become smaller. So you start from Vy and Vx like this. A little bit later time, you're gonna have, okay, this is Vx. You're gonna have same Vx, but Vy is gonna be smaller, okay? So if the initial velocity here is going like this direction, your new velocity here is gonna be bended a little bit because this component is getting smaller. So the velocity is gonna go this way a little bit. So, and as the ball goes up further, the Vx still is the same, and Vy becomes even smaller. So your velocity is going to be tilted along that direction even more. In the end, Vx is the same, but Vy, it's going to become zero because it's the same as free fall, right? So in the end, you're going to lose all these y components. So the velocity is going to be totally along this x direction, okay? So that's actually defines as the highest point for this motion. And then on the way back, this velocity is still the same, but you're gonna get a smaller, small component Vy going downward because the acceleration is going down. So, and then as time goes by, okay, I'm running out of place, but so you can see that Vy is getting bigger, you know. So you're gonna get, so that actually explains why you have this trajectory, you know. Okay, I'm not drawing very well, but you understand what I'm saying. So the reason is it got this kind of trajectory here is because the velocity of the object is being like tilted towards horizontal until it becomes fully horizontal, and then as on the way back, it's keep tilting like this, you know, because the y components, okay? Again, the x component does not change at all. What is changing is the y component. The y component decrease and then becomes 0 and increase, okay? So again, it's easiest if you can think about through the two components of the whole thing, which is quite complicated, okay? Okay, so let's talk about the example here, okay? So what I'm gonna do this example, the long jump example, okay? So what you have here is you have so what is given here is you have a long jumper. It leaves the ground at the angle of 20 degrees, and then a speed of 11 meters per second. So it's giving you the initial velocity basically. Okay, it asks A, how long does it take to reach the maximum height? B, what is the maximum height? C, how far does she jump? Okay, and D, let's just do the three part. Okay, so let's go back to our so it's 11, 20. Okay, so hold on, it's example 3.6. So here we have again, the first thing you should do is just draw a diagram which can help you to picturize the motion. So we have a long jumper, right? This is roughly how she moved on the air, and then you should draw a coordinate system. For a two-dimensional motion problem, you need to have two axes, and normally you set the horizontal one to be x and vertical one to be y, and then draw everything you know in the problem. So what is given here is the initial velocity, the magnitude, right? It's 11 meters per second, and then the angle is 20 degrees. 20 degrees. Okay. Now that's all given in there, and then it asks you a couple questions. A is the maximum height, and B is the time to reach the maximum height. Oh, sorry. Yeah, A is like the time to reach maximum height, and B is the maximum height itself. This time crash. Cooper, what do you say? Hello?
Sorry, Cooper, it was background noise. My parents are watching.
Background noise. Okay. C is Cooper, I'm sorry, you probably didn't get my email. This lecture started at 9:45, and because I misunderstand the time. So anyway, and C is how far it goes. Okay, basically horizontal distance, right? So we have these three questions. Okay, now how do we answer them? Again, we have some unknowns, we have something given. So when you make some connections between these based on the physics we learned, the physics relevant. Well, in this case, we're talking about the projectile motion. So certainly the physics involved here is projectile motion, right? So, but we have two directions now, okay? We have an X direction and Y direction, okay? Now, again, remember, nobody can solve a two-dimensional problem, at least I cannot, okay, without breaking down to components, you know? You have to look at the components. So, and it's important to know, when it's asking you a question, it's important to know that which direction it is asking you about, the X direction or Y direction, okay? So in this case, the maximum height, okay, the maximum height certainly refers to the Y direction. It's like, the time, right? So let's say this is delta t. Well, the time here, it can be either X and Y direction, because it's in both part of motion, you need time, right? The maximum height here is certainly about the Y component because of how high you go. Well, how far that's the displacement along the X direction, okay? So you can see here, they ask you something different, okay? So, and again, you need to be careful about, clear about what you have. Okay, so these two pieces of information are given, but this is not very useful for you because this velocity right now is neither along the X direction nor the Y direction. So you need to break it down into components first so that you can use them, okay? So this is our problem that we just discussed, right? So if you have this right here, This is gonna be your VI. This is gonna be VI X and VI Y. And then you have angle theta here, right? So what is given here is the length of VI is 11 meter per second. And then the angle here is 20 degree, right? So you're given this length and 20, the angle. You can find out these two components just like to our vectors. But in this case, it's a velocity vector. It's not a displacement vector, but it's the idea is the same. So VIX is going to be given by VI times cosine theta. So you have 11 meter per second times cosine 20 degree. And similarly, VIY is VI times sine theta, which is 11 meter per second times sine 20 degree. Okay. Okay, so let's calculate that. That's two numbers. Okay. So 11 times cosine 20, you got 10.3 for VIX. And then same thing for sine, 11 times sine 20. You got 3 point, okay, let me put, okay, got 3.76, okay. So these are the two components for the velocities, okay. Again, let me say this, okay. Whenever you have a two-dimensional problem, you see something like this given, always break them down to component first, okay. Without doing that, this won't help you to solve the problem because you don't, I mean, we have to look at the problem into their components, okay? Okay, so we got this now, right? Now let's see what else do we know? Okay, first of all, let's look at the y core component, right? Okay, the first question is about time, but it's the time to reach the maximum height. Because the maximum height is along the vertical direction, so it suggests us to look at the y component, to look at the vertical component. So pretty much, it seems like reasonable to look at vertical components for these two parts, and then look at the horizontal one from the last part. Okay, so let's look at this vertical component. Okay, so along the vertical component, what do we know? We know it's a free fall, right? And then, so this is our vertical component. So start from here, and then we know the initial velocity, right? This is a meter per second, okay? So we're given the initial velocity, okay, VIY, okay, which is 3.76. We're also given the, what else do we know? Okay, it seems like it's not given anything else, but there's some hidden information that you need to figure out. So again, remember, along the vertical direction is a constant acceleration, it's a free fall motion, right? So what is the acceleration? We actually know that, okay? It's gonna be negative 9.8 because that's the free fall acceleration, okay? Well, this is not given in the problem explicitly. You should realize this is the case, okay? And also we were given the, so what else do we know? There's another piece of information we know for this one, okay? What else? Can you guys figure it out?
The final velocity is 0.
Exactly. So we have VFY equals 0. Okay. Now, why is that? Because we're talking about the maximum height, right? The maximum height is always defined as when this component, the velocity is 0. Well, it's a two-dimensional motion. So even at the top, the x component, the velocity is still not 0, but the y component velocity is 0. Otherwise, it's going to keep rising. So we have these three pieces of information given. Okay. Now we're looking for delta t, and we're also looking for delta y. Okay. Okay, now, as you can see here, right, after we break down to this, it becomes a one-dimensional problem that we've solved before in our chapter 2 problems, you know. So this should become kind of a little bit familiar to you guys because this is all constant acceleration motion problem, and we're giving three pieces of information. We're looking for the first one like this, you know. Again, the point is we choose one formula to use out of the four formulas we have from our from the constant acceleration kinematics formulas, okay? Now we got 4 minutes left, so we won't be able to solve these together. So let me stop right here. I stopped a little earlier today because I want to go to the, as I said, I want to go to the physics workshop. I want to make sure that my Zoom can connect well. But you guys, if you want, you can go ahead and do this. Try to do this yourself a little bit as an exercise. I'm going to start from right here tomorrow, and then solve this problem, okay? And then we'll do some exercise together for these for this thing, okay? So I'm gonna stop. We will start a little bit early.